Hello everyone, it's May the 28th. It's a late session today. It's fine. It's been, I think, 10 days that I've been having this cough, and since I lost my voice, I think like the overall throat health has been bothering me for the past 10 days. And I think I finally start to see the light at the end of the tunnel, but still feeling very uncomfortable. But the voice is completely back. So that's good news. Well, I did something interesting today. I was on a website and I was trying to um, schedule for something online, but the scheduling website constantly shows me that all the spots have been taken. I mean, I've been on this website for the past, I don't know, 2-3 weeks, and every time I checked, it's either not available, right, or new slots coming out and then all taken. So I'm getting tired of it. So I know that it's possible for me to write some script to automatically refresh the page, and then you have to also do a couple of clicks to get into the page. So I know it's possible to write some script to do this. I just don't have the ghana to do it. It's just any library I'm going to use, like Selenium for Python. I know it's for Python testing web apps. I can use that to drive a web page, to refresh, select some buttons and click and then whatnot. I know it's possible, but it just involves some learning curves. So I decided to look for some Chrome plugins, and I think there gotta be some plugins that can do automatic refresh and automatic clicking. And indeed, I found two tools. One is for refresh, which allows you to refresh at an interval, and the other one is you can select the button from XPath. Actually, I don't know what XPath is in the past, but apparently it's an easier way to locate elements or tags or divs, whatever you call it, buttons, whatever you call it on a web page. So you can copy and paste the path or some other ways to identify the element into the auto clicker, and it will click for you with like a delay, certain amount of seconds of delay and stuff. So it took me like, I don't know, like 2 hours to set it up. The automatic refresh is pretty easy. You just set up a timer and then it refresh for you. But the automatic clicker is a little bit tricky to use, especially because I need to select a drop-down menu, and not just to select the item, but I also have to click the item. The clicker can select it. I can get it to select easily, but I just didn't have. I don't know how to select and click. So it took me a while in digging through. Actually, not the documentation. The documentation was not correct. I have to go through the issues on the GitHub. Thankfully, it's open source, and I got it. So it's working now. But I still hope that if I have time, I want to write the script myself, because there's still some functionality that's not provided by those two tools. I want to do it myself. But hopefully, I can get it scheduled, get the thing I want before I need to write this thing. Anyway, that's a little bit interesting thing happening today. All right, let's take a look at what we have today for the LeetCode. Maximum erasure value. You're given an array of positive integers and want to erase a subarray containing unique elements. The score you get by erasing the subarray is equal to the sum of its elements. Return the maximum score you can get by erasing exactly one subarray. Okay, subarray. What is a subarray? Subarray is not a subsequence. Subarray is continuous. As a subarray, it forms a continuous subsequence of A. That is, if it is equal to, for some error on, okay? So the largest is this, because, yeah, that's the largest. This one, you can do this, or 125, or 125. Okay, so subarray usually what? sliding window, but 10 to the 5th, see that? 10 to the 5th, if we do sliding windows, that's going to be taking a long time. But we can also do cumulative sum, right? Cumulative sum. We can definitely do cumulative sum to save the computation on the sum. So sum it once, and then we can get the sum of anything out. But now the problem is we don't know how large it has to be. And we also need a way to identify uniqueness. Interesting question. So the best, right? We can go from top down because we want to find the maximum, right? So if I have, that might not be true. I can't have some, hold on. Is it possible to have a sum with 2 values that's bigger than the sum of 3 values? Well, the sum of these 2 values cannot be extended to 3 values. Let's say because if you extend to 3 values, we're going to have repetition. Okay, like we say 101, all right? And then 101, everything is 1, and we have 100 in the middle. So in this case, I don't have it. We can have like, yeah, we can have all unique, but just surrounding 100, right? We have 100, 1, 2, 3, 4. The 101, 101, 1, 2, 3, 4, 5, whatever. Doesn't really matter, right? So given this array, then I just want to prove that it's not going to be going top down, right? So what I'm thinking about is 100, 1, 1, 2, 3, 4, 5, 6, right? This. I mean, if we go top down, we'll say this, right? Will be the results. But the answer should be 101, which is only 2, right? It's only 2. So definitely it's a little bit different. Okay, and this is still trying to go from like a greedy perspective, right? Going from greedy, we say when we find the most length, then we know it's not working. And another way to say is that we also always find the largest. But if we go for the largest, say this, right? We say it has to include 7, but the result is not going to include 7, so that also not going to work. So I think greedy in this way is not going to work. Dynamic programming, right? Dynamic programming, but how? Let's focus on this test. Let's focus on this case and see what we can find. Okay, so we have 5, 2, 1, 2, 5, 2, 1, 2, 5. Cumulative sum 5, 7, 8, 10, 15, 17, 18, 20, and 25 is a cumulative sum. Right? So we can use the cumulative sum to obtain the sum between certain 2 values, right? Okay, that's fine. Now, with that, we need pointers. So there gotta be a subarray as our target, right? So what we can say is like for each value, right? For each value, I am either in the subarray, the target subarray, or I'm out of the target subarray, right? If I am not in a top subarray, and the result shall still be the same. If I'm in target subarray, what I'm saying is we start from here, we start from the front, right? And then we say the target subarray is going to be, say, B5, right? And then we keep going. Now look at 2. So 2 can either be in the target subarray or not be in the target subarray. If it is in, so I'm going one by one. Which I'm saying is, if we find the maximum, how does the DB way of thinking this? What I'm saying is, if I find the maximum subarray in the previous, right? If I find the maximum subarray in the previous that we have encountered, now we add a new one, right? And that will depend on if this one is not going to be contained in. So this one, the new one added, can only participate in the array ending with this. So we just need to know the longest, right? Because we want, so we want to know the longest subarray ending with each value, right? The longest subarray ending with each value, the valid subarray ending with each value. And we add a new one. Excuse me. We add a new one. Then we can say either the new one can be appended to the previous one, now we get longer than with a new value, or the new one cannot append because it's going to be a repeat. Then the new one is going to form a new subarray, right, which is the one that we eliminate the repeating part. How does that sound? Because the subarray must be, like, it has to be the maximum length, right? So it's the maximum length ending at 1. This is the maximum length ending at 5. It cannot be even longer. It has to be the maximum one, the ending at 5. Yes. And then we just, every time we add a new one, we try to check. So we add a new one, all right? We can either extend, and if we cannot extend, can we, like, say by itself? I don't think it can be by itself, because if I can extend from the front, hold a sec. If I cannot put, like, say this one, this 2, right? So with 5 and then with 2, we say we can extend. And 1, we say we can extend. And now we got a 2. Now 2 we cannot extend because we have a 2 already. Do we start 2 by itself, or do we include 1? Well, we say that what we want is a subarray, the maximum length subarray ending at that element. If that's the case, then we have to include. Okay, so 2 will be 2, 5, 1 will be this, right? And then we have a value of 8, and then 2, we can only extend to 1. 5 again extended here, and then 2, can only do 2, 5, and 1, 2, 5, and 2, 2, 1, and then, okay, that's possible. How do we do the data structure? So it's gonna be what? I mean, I have to use a dictionary, right? So we need to check whether it exists, and we also need to check also need to know the location, the position, right? Oh, sure, we don't have to. We can just delete it. A set, right? A set. So, set of 1 to 5. I will record the value, and then this one comes in, and it cannot add, so we have to remove 2. Oh, we didn't know the 5 has to be removed as well. Huh. 5 has to be removed as well. Okay. So we need a dictionary. So keys will be the values. The value will be the index. All right, and now we got 2, so we find the index. So all we can do is things larger than that index. So we have to run a delete option, delete operation. That doesn't sound right to me, man. That doesn't sound right to me. If we operate only on index, right? But how do we check? How about we get the indices of everything, right? Indices of every element in it, right? And then as we go through, go through 2, right? So I know my index, and I just want to know if anything happened before me. So I go and look into the dictionary, and for dictionary I can use binary search to see where I am, right? Where I am, if there's anything ahead of me, and I see, oh, there's nothing ahead of me, then I can include it, and this one, and I found that there's something ahead of me, so I know I cannot include it. Then I need to say it has to be something right after me. Okay, that's fine. So I get index. Oh yeah, I think this might be working. So let's give it a shot. We're gonna create a dictionary. Oh, by the way, look at this. This beauty. This absolute beauty right here. This is finally I got. I think yesterday I was saying, how can I get the Monokai, right? I like Monokai. I really like Monokai. So I look online. Apparently we can install something called I think if I can pull it up, theme. Yeah, Monokai Pro, and then wow, so much Monokai to choose from. I think this one is Monokai Classic. I really like how this one looks like, and yeah. All right, so this is my thought. So first of all, we need to do a sum, cumulative sum, right? I think Python has a cumulative sum. I think it's itertools, or either itertools. No, probably functools. Yep, I think that's functools. Let's try functools. How to. I don't want how to. I want this. Maybe it's not. Maybe it is a tool. No. Cumulative sum. Python. I think they have one. It doesn't have one? Really? I don't believe it. I feel like I've seen them before. Try again. Yeah, here. Accumulate. I think accumulate is the cumulative sum. Yeah, accumulate. So import itTools, right? Definitely this is going to be a list itTools dot accumulate iterable nums, right? And we also need a index map, right? This will be a default dict import collections, right? This one's going to be collection dot default nope default dict list. Okay, so for I and enumerate nums index map, we're gonna n dot append I, and it's already sorted, so that's good. So I have this, good. Now what we're gonna do is iterate through nums again, and we need what do we need? Import bisect. We're gonna do binary search. So we're gonna go through nums. We're gonna keep a front and back, right? Left and right. So left gonna be 0, right? And then we just say actually that's fine. Left is 0 for right in range 1 to land nums, right? So every time the right comes out, so we're gonna say value equals nums r, right? Nums right. Then we're gonna find to see if there's anybody ahead of me, right? So what we're going to do is do bisect dot bisect. Okay, we'll do the right or left. So this is going to be matching, right? So what do we want? Insert. I want bisect left. Bisect left. Yeah, bisect left. So what is the bisect left? Sequence is going to be index map value, right? And value. No, R. Right? So R, put it in, and then it will match, but it will return the index. Actually, it's return the index myself because I'm inserted ahead of the matching value, right? So if I match the first one, yeah, if the first one I see, so I match the first one to 0, right? So that's actually fine. What is not fine is if it's not 0, that means somebody is ahead of me, right? Yeah, we always look for the one right before me. Hold on. So we find something. Hold on. I'm a little bit twisted right now. So we do the bisect, right? We do bisect. We can find the index right before me that occurs, right? And then what we need to know is whether that one is in the current range. Yeah, whether that one is in the current range. So this bisect left, this one gives us the pre I, right? So the previous occurrence of the index. Now, if the previous occurrence is 0, no, it's not going to be 0. Yeah, it is going to be. So the previous occurrence. So this is the index of the list inside index map file, right? So it's different, right? It's different. So it should be this one minus 1. That's the previous index because I say if I match then I insert ahead of it, which basically means which is report exactly the same index as the matching one, right? So I do -1, that's going to be the previous one. Yes, so it's going to be that. And we say if we say no match will be pre-I is smaller than 0, right? That's a no match, or index map val pre-I is smaller than my left, right? So it's out of the range, right? It's out of the range. So if it's out of the range, then that means we can include, right? We can include the current R, which means our result. So we're gonna put result here, which means our result is going to be I suddenly realized the left. I have to do left -1, right? Yeah. So the result will be, what's the current result? Res equals max res and cum sum. We can include R minus cum sum L -1 if L is larger than 0, else 0. Right? So we can update the result. Else, which means pre-I is larger than 0, larger equal to 0, and larger equal to 0, and this thing is larger equal to L. And that means we are inside the range. So if we are inside the range, then that means we need to update the left, right? That means the left has to be updated to the value right after. So it's going to be index map val pre-I, right? We know that one is larger equal to the left. So but I can now use that one, so it has to be +1, which means I should change this one if this is larger equal to 0 and this is larger equal to L, right? If that happens, then we say we update this and we always update the rest after each step. Okay. Let's think about this. Is it larger equal to L? L is the left boundary, right? The left boundary. What if I have all the same letters? Well, if it's the same letters, then it will go inside or find as a 0, right? So we will say, I'm going to put it here, -1 will be 0. So 0 larger equal to 0. So no, update. And after update, current. What if L and R is the same? That's fine. Right? Then I go all the way down and then we return rest. Alright, let's give this a shot. See how we go. Alright. So I think I can just manually type it. 4, 2, 4, 5, 6, 17. That's way too much. Copy and paste. one gave us 8. I think I also create a custom test case. Actually, not this one. The one we have is 101, 100. Right? And, ooh, way too many. This one. Yep. And we have to fix this. Okay, so here we need to change this to nums. This is going to be maximum stuff, nums. Alright. We're past first two. Oh. That one should be 101. Okay, we passed the first two, but we failed the last one. That's strange. That is strange. Why? Why is that a case? The rest should get 101. Okay, let's take a look. As usual, before we start, we can always get a cum sum and get index map. Cum sum is correct. Index map looks fine. Okay, so left is 0, R is 1 to land nums to here, alright. And then value is nums, value is 1. Pre-I, bisect, map 1. So 1 will return 0. 0 minus 1 is minus 1. And then I say, ooh, there's minus 1. So we say res equals res, comes some R, 101, minus, comes from this, if, probably just lack a parentheses. Yep, that's a lack of parentheses. And now I think we passed all 3 test cases. Okay, so now we're gonna try some more dramatic, weird test case. So we're gonna do some keyboard smashing. This is our one type of test case that I need to do, this keyboard smashing. Alright, try it. Oh, I got too big a value. To 10,000. It's way too big. Okay, this one passed. Alright, now what we're gonna do is, oh no, that's not my intention. Like lots of repeats. Tons of repeats. Alright. See if I can handle. Okay, no problem. Alright, edge case, I think the least number is 1. So edge case 1. Oh, I see. Rest should be nums 0. Yep, should be nums 0. That is true because we start from here. Okay, this one shall be right. Nums 0. Alright, what else can we test for? I just submitted. Let's see. Pending, judging, accepted. But looks slow. Looks slow. So we got it, but it's kind of slow. So how do we say? So this command is we use cumulative sum to compute. Actually, do we need cumulative sum? Yes, we do. Yes, we do. Because we're doing left plus 1. Hold on. We're doing left. No. We're doing not left plus 1, this plus 1. So we are throwing away some values. So we don't know what those values are. We just throw them away. So yes, we use cumulative sum to facilitate the computation of the sum of any array. We build a index map to to know what indices any value occupies. We keep the indices sorted such that when a value is encountered, as we loop through nums, we can use binary search to locate what index to locate the index of the previous occurrence of the current value. Now when we loop through nums, we keep a left pointer and a right pointer. Right pointer always marches forward, and each time we will obtain the index of the previous occurrence, right? The previous occurrence. If the pre-index is out of the range of left pointer, it's to the left of the left pointer, that means the current value can be included without repetition. I spelled it wrong. Repetition. Otherwise, we must shrink the left pointer to the index right after the pre-index. As we loop through nums, we keep track of each valid subarray sum. Keep track of the sum of each valid subarray and return the result once nums is depleted. Okay, so we took on to build this. We took on to build this, and we took on to run this, and each time we have to do on. So it's on log n, right? On log n, or log n for the binary search, and the rest is O1. So O1 log n is the runtime. Take a look. We are at 1,152 milliseconds, or a 17% ranking. All right, I'll be right back. Yeah. All right, I'm back. So apparently we are not doing very well, right? It's only 17%, but look at this runtime. It does allow for a long runtime. Okay, so maybe there are better solutions, but I think this is pretty neat, right? I'm actually pretty proud of this. Look at that. I think it's pretty good. All right, let's take a look. Maybe there are better ways. No, actually, I think there gotta be better ways. Very, very rarely do I come up with the best solution. I think it's gotta be a medium. Yeah, it's a medium, most likely a medium. So what's the number? 1695. 1695. 1695 must be a contest. I think it's a contest. Sliding window and hash set. Oh, O-N. See? O-N. How do you do O-N? Two pointer with hash set. All right, let's take a look. Oh my God, so easy, huh? So easy. Okay, set new hash set. Sum answer J I and J. So 2 pointers. If set does not contain nums J, sum plus num J, answer equals this. Sum dot add else. Sum equals sum minus num. Really? That's it? Huh? Really? This is so simple. So we keep adding until we cannot add, then we remove. We remove I and I plus plus. Hold up. We remove I. Huh? It's sliding window, right? So we keep going J, and then the next J is contained, the value is in the set. But we don't know where in the set. We just know it is in the set. And then I say, I'll remove I, move the front. I see. I see. I have done this before. I have seen this before. I have the same reaction before. I got amazed by the same algorithm over and over again. I just cannot replicate it myself. I see. We don't increment J here. So every time J is in it, and we just keep removing the front. My goodness, yes. Yes, that's how you handle the... So instead of doing a binary search to look for the... Have I done this before? No, I have not done this before, but it looks very similar to the question that I had before. I think I used the exact same solution in the past. I used binary search to look for the index of the previous occurrence, and then I look for the solution, and I see it. You don't have to do that. You just let's see if I find the example. 2 pointers, right? So the right point keep going, and when I find something, right, then I move the left point, right, and I just remove this. Oh, it's still in. Remove again. Oh, it's not in. Then I keep removing this. That's it. Yeah, just the right keep going, if I find something that's in the left, there's a left to go until we remove the thing. Ah, my dear Lord. I have absolutely done something similar before. I have absolutely say something, probably even in the live stream. And still, still unbelievable. Just cannot, right? Just cannot memorize these things. Like binary search is always the first thing that comes to my mind, but set is such a different stuff. Come on, man. When I say subarray set, right? And rest is 0. And sum when you rest, when you s, right? And now we say while I smaller than n and j smaller than n, right? We're not say if nums j not in subarray set dot add nums j I have to add in nums j. I'm going to do s plus equals nums j as well, and then res equals max res s. After that, j plus equal to 1. Right? This is when j can be added. Else, j cannot be added. J none of j is inside, right? It's inside. Then what do? Then we do subarray set dot remove nums I. S minus equals nums I, and I plus equal to 1. Going back, if it's still inside, I remove another one, and back. It's not inside. Hold up. We start both at here, right? Then we add num j go forward, and then this is not inside. Set add this, s add this, and j go forward. Okay, then j go forward. J is here, right? J is here, and then we say remove this, s minus this. Okay, going back again. 2 is still inside, so remove this. I come back again as here. Now j is not in subarray. Then I will add 2 again. Now I add too much. How do you prevent this from happening? Right? I'm going here, coming back here, and oh, because it's not in there yet. But j I haven't added yet. So j is pointing here, but this one hasn't entered yet. So it's already it's only 521. It's only 521. Yeah. This will work. And we return res. Right. Yep. Pass everything. This is the ON solution with sliding window. I have definitely seen this before, but unfortunately my initial go-to is still binary search. Gotta memorize this. I gotta incorporate this into my repertoire, right? It's a good solution. It's a good way of doing sliding window. This is sliding window. That's what sliding window is. You slide on the right and slide on the left. God, can't make it. Not a happy result. But we did do it. Okay, so this one will be faster because ON. Yeah, faster. All right, I think that's it. I think that's what everybody else is talking about. Sliding window with hash set, sliding window with hash set, 2-pointer with hash set. Yep. Somebody do a prefix sum. Or is that a different solution? Oh, what is this? Is your hobby to use fake accounts to download other posts, upload posts yourself? Wait, what? Drama. Not interested. Prefix sum. What is this? I have padding, prefix sum, and last equals max last nums I is the index array. Oh, that's O n squared. This is O n squared. It's the same as this, but I use binary search. They just use a max to find the last occurrence, I guess. To find the last occurrence of nums I. Why you use? Isn't that the last? Wait, do your last go? Oh, last go here. Oh yeah. Nums I, and this one will give me a index array. It's the last occurrence, right? I think this is the last occurrence. Okay, the last occurrence, and max answer pre-I minus prefix sum. Oh, okay, yep. I think that makes sense. Yeah, but I like this one. I like this one. Sliding window. All right, that's it. We got a sliding window. We got to memorize sliding window, and we have our own solution. All right, I'll see you guys tomorrow. It's gonna be a difficult one tomorrow. Get ready. Adios.